Hello, for this screencast, we're going to spend some considerable time on item number 16.11 from the text. This is from week 3, and in this screencast, going to do a couple things. First, I want to talk briefly about the overall big picture of an ANOVA, a single one-way ANOVA, which is the type of problem we're working with here in Chapter 16. And I want to walk you through how the textbook shows you how to do this by hand, um, and not to make it a pain for you, but I think it is valuable to see what's actually going on. And if you did it by hand, you can follow my example also to kind of compare, since this is not an item that has an answer in the back of the book. And then the other part of this video is to walk you through how you can use Excel and the data analysis tool pack to produce the single factor ANOVA, like I have here in this picture, and how to use pieces of that output to answer the follow-up questions in item 16.11. So hopefully this helps with basically 3 major ideas. So first, let's take a look at the data that we have. This chart up here deals with the problem in the book, which was the number of driving errors based on the number of ounces of alcohol consumption from the drivers. And this chart is set up such that there were 5 samples of each treatment, meaning that there were 5 individuals that had 0 ounces of alcohol consumption, and this is the number of driving errors they had. And then you had individuals with 1 ounce of alcohol, and these are the number of driving errors they had, and so on, all the way up to 6 ounces. And whenever you have any type of data, you're going to have differences. You're going to have variation between them. But when we're running an ANOVA for more than one pairing or more than 2 samples, in this case here we have 5 different samples, 5 different categories, or 5 different treatments, if you will. We want to see, is the variation between these groups, between these different categories, greater than the variation that we see within each of these groups. So within each of these, they aren't all the same. Not everybody came up with only 1 driving error, all right? And here for 1 ounce of alcohol, not everybody came up with the same number of errors. So there's variation within these groups, and we can see them just from looking at it. But you also notice from this group, probably at first glance, that you realize, there is something going on here. The more ounces of alcohol, the greater number of driving errors. And you can see within here again that the variation between these groups seems fairly large, between a 20 and 1, between a 20 and 4. However, there are many times that you have data where you have, hundreds of data points, and maybe the values are too close to call from just looking at it. So we are going to run what's called an ANOVA, and it allows us to compare against the null hypothesis, where the null hypothesis is stating that there is no significant difference between these values. And the alternative meaning that the null hypothesis is not true, that there may be at least one pairing, that there's a significant difference. What I did down here was, I actually, just for the case for this video, is I took these same values and I rearranged some of them to show that you can have the same data points, but they're spread out throughout these different groupings, meaning that the overall variation is no different. These are the same values, so the variation between all the different scores should be the same between these. But the variation between these groups, between the different treatments, in this case here is going to be a little less. So first things first, let's take a look at how the textbook walks us through taking these values and crunching these by hand. This first screen what I did was I took the information that they gave us and tried to compile it all into the type of data points that we're going to need to do this by hand. We have the totals of each of the groups. Up in purple here is 0, 1, 2, 4, and 6. That just coincides with the 0, 1, 2, 4, and 6 here. But the totals for each of these were the sum of those columns of 15, 20, 26, 56, and 74. Capital N, if you recall, is the total number of sample spaces. So there were capital N meaning total. There were 25 different samples, and in each one of those groupings or each treatment area there were 5. So the lowercase n is the sample size of each of those within the groups. Then we have different degrees of freedom. Degrees of freedom of the total is 1 less the total number of sample space here, so 25 minus 1, which is 24. The degrees of freedom between, this means that, okay, if I have 5 different categories, there were 5 columns or 5 treatment areas, 5 minus 1, which means I have 4 degrees of freedom between. And then the degrees of freedom within, this is a statistic that is set up so that it's the total sample space, which was 25, minus the number of categories. So the 25 minus 5 gave us 20. The item number 16.11 didn't actually specify a level of significance or a degrees of freedom, but it did reference to the item that it came from. I think it was 14.14, and it had a an alpha or level of significance of 0.05. So I'm going to stick with that. And then also, these are values that the textbook gave us in the problem, and they're useful in the formulas here. I'm not going to verbally walk through all of this, but basically what I did was I took the sample that they had on a previous page, that gray chart that walks you through all the different processes, and I followed the steps, step by step here, to come up with these values. So the sum of the squares between was 513.16. And again, I followed the formula that they gave us here. This might be a good place for you to pause. But basically, what I did was we have the sum of the squares between, we have the sum of the squares within, and we have the sum of the squares total. One little quality control check here is the fact that these two values, the sum of the squares between plus the sum of the squares within, should give us the same value of, in this case here, 911.176, which is the sum of the squares of the total. So at that point I realized, all right, I think I have all my data correct. Then we converted these sum of the squares, and we had to find the mean sum, the mean for each of these for between and within. And you use the values from this previous information. So the mean sum of the squares, or I could say that the mean standard error was the sum of the squares from between divided by the degrees of freedom between. So between matched together. So 513.16 divided by the degrees of freedom of between, which was 4. That gives us that value. Same thing for within. So the mean standard error from within was the sum of the squares within divided by the degrees of freedom within, which gives us this value. And our F statistic, or our F value, is the ratio of this mean divided by this mean. So I divided the two of them and came up with an F statistic of 6.44. I'll pause there.